Okay, let's see. Are we recording? Yeah. Okay, good. Okay, so here's where we left off. So we were talking about graphs and level sets and stuff like that, and the big point of which was to make sure that everybody recognizes that this is not going to be one of those classes where there's a single, consistent, reliable, take-it-to-the-bank relationship between algebra and geometry. Right? When you write algebra and then you draw a picture, in Calc 1, that's always the same kind of picture. You can always interpret it the same. The geometric interpretations of the calculus are always the same. Okay, not so in multivariable calculus, and you got to make ultra sure. I mean, really double check, make a conscious effort to always confirm before you start doing calculus. Wait a minute, what kind of a picture am I looking at? If it's a graph, then calculus will have certain geometric interpretations. If it's a level set, there will be totally different geometric interpretations. And this is super duper important. I've taught this class many, many times. I've seen students crash and burn on this so many times, and that's why I hit it so hard, right? And I know I'm emphasizing it more than the book does, but this is why. Okay. All right. So moving along. So this next topic of rotations is the first in a short list of tools that I want to give y'all for how to understand an equation that involves three variables. Right? So y'all have seen, again, back in high school, etc., a bunch of different, methods and tools, etc., for how to interpret an equation of two variables. Right? With three variables, the pictures are three-dimensional. There's going to be different methods that we're going to need. And to emphasize, this is not going to be an exhaustive list. This is not going to be a list that will allow you to interpret every single possible equation of three variables. Absolutely not. Way too hard. Couldn't possibly. All right. So, but nevertheless, there's a few tools very useful. So here's the first one. It concerns rotations, and here's the big if. Let's underscore that. If this happens. How often does this happen? Sometimes. Right? But if this happens, the x and y appear in the equation only, big emphasis there, only as part of this expression. Just to be extremely clear, I'm not saying if this expression shows up. That's not enough. I need to know that this is the only way that x and y show up in your equation. If that is true, then your surface is rotationally symmetric around the z-axis. And that's a huge piece of information that's going to allow us some big advantages in how we identify what these surfaces actually look like. Now, let me try to persuade you this is actually true. So let's entertain, suppose we got some equation that has this feature, that x and y appear only in this special form. And now let's look at this point. And let's imagine this process of kind of rotating it around, and as it rotates, it'll generate a bunch of other points, for example, that point. So two different points. And they're different points. And so they have different coordinates. And x and y are different for these 2 points. And it's tempting to say, well, if there's different x and y coordinates, you're plugging in different values into an equation. They're going to be totally different arithmetic, and who knows? If one works, maybe the other one doesn't, and vice versa. How could we possibly know? And the point here is that x and y appear only in this special form. And so even though these 2 points have different x and different y, they have the same distance from the z-axis, because one is a rotation of the other around the z-axis. That was the whole point here. Right? So even though there are different coordinates, they will have the same values of they will have the same values of this expression where the only places x and y appear. And of course, they also have the same z coordinate. So as far as the equation is concerned, these points are going to be evaluated by exactly the same arithmetic. So they're either both on the surface or neither is on the surface. And the nice conclusion we get from that is, okay, well, these points were rotations of each other. That means our surface kind of has to be rotationally symmetric. Okay, so it's a lovely little conclusion to be able to draw. One of the things I really like about this is that this part, right, the rule, right, the deal, right, what you have to check is eyeball glance trivial. It's so easy. Just look. See if there are any X's and Y's that don't fit that form. Costs you almost nothing. You can do it in a fraction of a second. And then you get this conclusion, in exchange for that very, very low price, you get this powerful conclusion of rotational symmetry. Now, we're going to combine that with this next observation, which is, and this is just a geometric appeal. You just have to think this through, so take some time as needed. But if a surface is rotationally symmetric around the z-axis, right, if it's literally rotationally symmetric, then it is a rotation. And furthermore, it's a rotation of its cross-section in any plane containing the axis. As again, just geometric appeal. Let me show you an example of this in action. So let's look back at this equation right here. Now you may recall last time we were talking about this exact equation because it is, it showed up as, anyway, the graph of this function. And I was making some observation about the relationships between graphs and level sets and horizontal slices and all that business. Okay, so I just asserted what I claimed this surface looked like, and I said, trust me, and we'll talk about it later. All right, so here we are. So, all right, step one, to understand this surface, I claim it's rotationally symmetric around the z-axis. And now you may quibble and say, I don't see the square root in there. Isn't there supposed to be a square root? But do keep in mind you can rewrite this equation as z equals square root of x squared plus y squared quantity squared. So, if you can write the equation equivalently in different forms, any form that satisfies the rule, you're all good. Okay, so this has the feature that x and y appear only in the special form, so we instantly know this, whatever this is. I don't know what it is yet, but whatever it is, it's rotationally symmetric around the z-axis. Again, because x and y appear only in the special form. Okay, so I'm going to draw the z-axis right there, and just to emphasize that that's the axis of rotation. Again, if it's rotationally symmetric, then it is a rotation. I can pick any plane containing that axis and just look at the cross section in that plane, and then it's rotationally symmetric, so I'll just rotate that cross section. So, okay, how do I do this? Let's suppose I decide I want to take the cross-section in the YZ plane. Arbitrary, by the way. I had a bunch of choices. I could have chosen the XZ plane, or I could have chosen some plane at some angle through here. All right, a bunch of different options. Any plane that contains the Z-axis, I strongly encourage you. Take pity on yourself and pick a coordinate plane. Life becomes a lot easier, right? So, for no particular reason, I am going to pick the YZ plane here. And how do I take that cross section? Well, the YZ plane has equation x equals 0. I'm going to stick that right in there. And my equation becomes this, z equals y squared, and flashbacks to high school algebra 2 or whatever they call it these days. That's a problem. That's no problem. Everybody on board? All right, so my surface is rotationally symmetric. I know that this is the cross section. I know that I can therefore generate my surface by rotating this cross section. And now we have this really, I'm going to say easy in this case, geometry challenge of visualizing, well, what do you get when you take this curve and rotate it around the z-axis? And I think it's a pretty easy pitch that what you get then is this kind of bowl-looking shape that I claimed last time. And side note, this is called, let me get this just a little bit. There we go. This is called a paraboloid. Does everybody see the method there? I mean, again, kind of a three-step process of analyzing, the key point of which was to recognize the rotational symmetry when it exists. All right, so repeat. You can do this to any number of different surfaces, and here's another nice example. Actually, let me make my screen bigger. There we go. So let's look at this thing. And okay, weird. I don't know what to do with that minus sign. And it's vaguely suggestive of maybe a hyperbola or something. But yeah, but how does that actually work? Okay, so same process. I'll be quicker with this one. X and Y appear only in the special form, so it's rotationally symmetric around the z-axis, which means I can pick any plane that I like that contains that axis. Now, just to mix it up, let's pick the xz plane, which has this equation, which I can toss into there, which then becomes this, which we all recognize as a hyperbola, specifically that hyperbola. And again, now the old geometric challenge of, okay, you got to visualize and just use your geometric intuition here. What do you get when you take this orange curve and rotate it around the z-axis? And the resulting picture giving us that surface is something about like that, and this is what we call a hyperboloid. Specifically, a hyperboloid of one sheet. You'll see momentarily why we call it one sheet. Okay, how we doing? By the way, if you're a little rusty, let me rephrase that. For the very large fraction of you who I'm sure, if you were anything like me when I was in college, if you are rusty on, wait a minute, which way does the hyperbola go? Does it open up that way or this way? And it's easy to get that, confused. And by the way, if you want to memorize your way out of that problem, I will point out the awkwardness of what if the one is on the other side of the equals instead of this side, and then everything changes. And right, so try to have a bulletproof system in your head for how to understand hyperbolas. Right, make sure it's not too rigid so that you're going to inadvertently get confused. But anyway, make sure you're good with that. If you're not clear on how to do that, on how to, how do you know which way the hyperbola goes, come to office hours. Be very happy to explain. No problem. Right? I have my own little hack, little trick that I think works really well. Anyway, make sure you're good with that. And notice this question's really a lot like the previous one. Note the symmetry, take a cross section, rotate it. Turns out it works very nicely around other axes as well. I'm going to say it's exactly what you would expect. It is a lovely exercise to think through how would you argue something analogous to this argument here, but where the rotational symmetry is around the y-axis or the x-axis. It's going to be totally analogous. The picture is going to be different. Think it through. It's a good exercise. Excuse me. The punchline is that if any pair of variables appears only in the special form, and you'll notice that's what we have here. Now here it's y and z that appear only in the special form. Then you have a rotational symmetry around the axis of the other variable. So y and z in the special form, the rotational symmetry is around the x-axis. Now, I think that's pretty believable, but again, make sure to think through that argument. Okay, same game then. Let's see here. We'll think about a cross-section. Pick your favorite plane that contains that axis. Whatever, suit yourself. I'm picking the XY plane here for no particular reason. If you want to do the XZ plane, that's good. Any plane that contains your axis. Right? So anyway, I'm picking z equals 0 And I can plug in z equals 0 into that equation pretty easily. That gives me this, again a hyperbola, again flashbacks to high school algebra. That's your hyperbola. Now you think about what happens when you rotate this curve around that axis, and the conclusion is that this, aka this, looks like, ugh, and then this is a hard one to draw. This is an art challenge, but it's kind of vaguely like this. I don't know why, but to me, I see, I call this the staring contest. This is like two contact lenses of two people who are like trying to stare each other down. They're looking their eyeballs right into, I don't know, that's what I see. Right? But anyway, it's that's what it looks like. And you'll notice that this, again, is a rotation of a hyperbola. So again, we're going to want to call this a hyperboloid. But now you'll notice that there are two sort of distinct chunks in this surface, whereas up here there was only one. What's going on here? My stylus. Oh, come on, did I run out of battery already? That's ridiculous. How could that be? Is my finger... See, my finger works. Oh, man. Okay, I don't know what's going on here. Just plug it in. It'll be fine in a few minutes. Okay, we'll use the backup stylus. So one sheet, because this surface comes in one chunk. Pretty believable, right? Okay, a million other examples, some of which are homework exercises. This is the argument, and it applies in a lot of circumstances. Okay, next tool. Deformations. So this is another important idea. This is another situation that comes up quite a bit, surprisingly often. And that is that you're being asked, let's say, to figure out what does a particular surface look like, and the equation is really, really similar to an equation that you already know what it looks like. Right, so that's the scenario we want to entertain here, and we'll start by noticing that this equation right here is pretty easy to understand. After all, I could notice the left side of the equation is just rho squared, right? So that is distance squared from the origin. So that whole equation basically says distance equals 13, and I know what that's going to give me. That's going to give me a sphere, like so. So that I already know. Okay, so the big question then, what happens geometrically to the surface if algebraically everywhere I see a z, I replace that with 2z? So you'll notice that's what I did here. This z, everywhere I saw a z, I replaced that with 2z. And again, very specifically, it's not just typographically, right? You look at the z, and whatever it is that is happening to the z happens to the 2z. So this is 2z quantity squared, not 2z squared. Right? So specifically, the z and everything that happens to it is replaced with 2z. Okay, so that's the question. We have a known surface with an equation. We tweak the equation in that specific way, and the question is what happens geometrically to the surface. And I'm just going to argue this by sort of example. You can confirm yourselves that this point, if you plug it into this equation, works, but it doesn't work over here. Of course, it changed the equation. So 3, 4, 12 doesn't work. Now let's let's just speculate. Why didn't this equation on the right work? Well, because of the 2, right? I mean, look, what was supposed to happen is this 12 was supposed to get squared, and that's not what happened over here. The 12 got turned into a 24 before it got squared, so of course it didn't work. So the idea of what you can do is just try to anticipate and account for that, sort of undo it before you do it, in some sense. And so the cool observation is that even though 3, 4, 12 doesn't work, 3, 4, 6 does work, because this whole business about multiplying by the 2, yeah, I saw that coming, right? I turned the 12 into a 6. Putting 6 there then makes this 12 getting squared, which is what was supposed to happen in some sense, arithmetically. Okay, so so that's the nice effect, and let's see here. Let me get rid of the mess. The big conclusion is that all of my z coordinates get cut in half. Right, what had been a 12, I just turned that into a 6, and this gives me a one-to-one mapping of every point on the surface described by the original equation. I can, by this process, turn into a point that satisfies my new equation. So, said differently, this algebraic move causes this geometric consequence. Everybody on board? So the specifics of this example are just the tip of the iceberg. In general, the way I like to write this down here, whatever you do to an equation, specifically, whatever you do to a variable in an equation, the opposite happens in the surface. So, really nice little rule there. So, for example, let's suppose I want to make sense out of this equation right here. And you look at this equation and a lot of questions pop up. Can I use a rotational symmetry argument? Not really. I see some x squareds, I see some y squareds, but they have, I don't see x squared plus y squared. There's constants in there messing it up. And no matter how you try to move things around, unless you get lucky and a and b happen to be equal, you cannot write that in terms of just square root of x squared plus y squared. You can't do it. So I can't make a rotation argument, and by the way, play the same game around the y-axis or the x-axis, and again, crash and burn. You cannot make a rotational symmetry argument on this. So what can I do instead? Well, I can instead say, look, here's a similar equation that I already understand. That's this. That's, super easy. And I can observe that the only thing that happened between these is I effectively, for example, replace the z with z over c. And as a result, then, I claim the effective consequence of that little algebraic move is to stretch things by a factor of c in the z direction. And then, likewise, this fact that I replaced y with y over b, well, that stretches things in the y direction by a factor of b. And then likewise with the x's, I guess I'll go ahead and do this. So the x gets replaced with x over a, which stretches by the factor a in the x direction. So no rotational symmetry argument here, but I can view it as a tweak of something where I do have rotational symmetry arguments and spherical coordinate option. I can reduce it down to an option where I've got more tools to work with. Solve the problem where you've got the tools, right? Do most of the heavy lifting happened right here, where life was good. And then just keep in mind how this adjustment affects your answer. So really, really cool idea. Again, I think undersold and underappreciated. This is a really neat trick. I think they do make some quick mention of this in the book, but not as much as I would have liked. So more examples, and I'm going to let y'all read these. They're pretty straight reads. Do be careful about one aspect of this one. A lot of people misunderstand, don't really play the algebra quite right. A lot of people look at this and think, oh, I'm replacing x. It looks like I'm dividing by a squared, right? But nope, that's not right. We are not dividing by a squared. What we are doing, and you can see it more easily if you rewrite this algebra a little bit. Let me rewrite all of this as x over a squared plus y over b squared. And now it's easier to notice that, in fact, the x is getting replaced with x over a. So do be very careful about that algebra. It's easy to mess that up. Anyway, we already knew this was a paraboloid. We can see that this is therefore, well, just whatever you get when you take that paraboloid and kind of stretch it in the x direction and stretch it in the y direction. And so instead of having circular cross sections like this did, this will have elliptical cross sections, and that's what we call it, an elliptical paraboloid. Okay, and likewise down here, again, pretty much the same deal because of all of this jazz down here. This is an elliptical hyperboloid of two sheets. Details to be checked. Make sure you do that. It's good exercise. How are we doing? All right, moving along. Okay, excuse me. So on to the derivative. Let's see if my better stylus is working. Yep, I don't know what happened there. That's weird. Okay, so let's talk about derivatives. Finally, get some calculus done in this course called calculus. Before we get to specific derivatives, here's a surprise. There's actually lots of kinds of derivatives in multivariable calculus, and this is not, I'm going to say it's kind of unexpected. If you look back to single variable calculus, single derivatives only, right? No, let's not talk about higher order derivatives. If you're looking at single first derivatives, there's really only one such concept in a Calc 1 class, right? And not so in multivariable. It turns out that there are several different ways to think of something, write down certain mathematical objects that, in their way, in very meaningfully and naturally and usefully could/should be called derivatives. And there's several of them. And they're related, but they're importantly different. Right? So just keep that in mind, and that is weird. It sort of brings up the semantical question of, well, if they're different, why do we use the same word to describe all these different things? And the reason is because they have something in common. They're variants of the same basic idea, and so what is that basic unifying characteristic that justifies calling all of these things by similar names? And the answer is right here. As I see it, this is a personal point of view, all of these derivatives relate input changes to output changes in some way or another. So this is one of the big, if I had to make a top 10 list of most fundamental, takeaways from this course, this is on the list. Right? I think it's a really big deal. All derivatives, whether you're talking about partial derivatives or gradients or total derivatives or derivative matrices or derivative transformation, all these various different things that use the D word, in their ways, they all relate input changes to output changes. All right. Okay, so that's just a perspective thing. Now let's move it along. We are going to start with partial derivatives. I think it's worth recognizing why we are going to start with partial derivatives. Let me give away the ending. It's not because that's the best choice, necessarily. There are some nice features of partial derivatives. They are easy to compute. I like that. That has an appeal. It's an easy on-ramp into the world of multivariable derivatives. They are familiar. They kind of look a lot like single variable derivatives. So again, easy on-ramp, and that's nice and all. And, pedagogically, not for nothing, the book does it this way, and anytime you deviate from the book, there's a little bit of a cost of, potential confusion. So there are good reasons, and that's why I will start with partial derivatives. But I will point out, that does not mean that this is pedagogically best. And it also does not mean that that these are what should be your fundamental point of view on multivariable derivatives. In fact, I believe quite strongly they should not be your fundamental point of view on multivariable derivatives, right? So as we go through this discussion of partial derivatives, just keep in mind this is kind of a naive first thing to try that's going to have some merit, but this is not the big concept, and this is not where you should, conceptually hang your hat of how to think about derivatives. It's a first attempt that is not a total failure. I think it's a pretty good way to think about it. Okay, so let's go on with this first attempt. Here's what we're going to do. Got this function that has a bunch of different variables I don't know how to deal with. I think back, pleasantly to the convenience of the old days when I only had one variable to deal with, right? Now I got all these different variables. Wouldn't it be nice if there was just one variable? And so with that in mind, we're just going to choose to hold most of those variables constant. And if you think about it, if you have a variable that's not allowed to change, is it really a variable anymore? Isn't it kind of a constant if it's not allowed to change? I think it's a constant, right? So we used to have a bunch of variables. Now we have just a single variable that's actually acting as a variable, and therefore I am now looking at a single variable function. Right, we started with a multivariable function. Now I've got a single variable function. And then step two, just take the usual derivative. That's all a partial derivative is. And remains to be seen why we care and how to make sense out of this. What does it look like geometrically? We'll talk about in a minute. Okay, so a little bit of notation. We just have to get this done. That is probably the most common standard notation for a partial derivative. It looks a lot like Leibniz notation for single variable derivatives, right? But because, very importantly, we're doing this weird move, right, where we're just pretending that a bunch of the variables are constants, that's make-believe nonsense. I can make-believe that, but I can't assert that as just straight up true because it isn't. Right? I'm making a very significant choice there. So in recognition of that, we cannot use D's here. You cannot write this as an actual, literal, single variable derivative. So you gotta use this little weird symbol down here, and just to emphasize that symbol, it is not only not a D. It is also not a lowercase Greek letter delta. A lot of students get confused on the symbols and think it's a lowercase delta. It's absolutely not. Lowercase, for one thing, the lowercase delta kind of hangs over on the right at the top, right? But it's just literally not that symbol. So it is not okay to, I just choose to write it this way. Nope, not your choice. You can't. It's not. That's just not what it is. And likewise, you cannot write it with a D. Not okay. So this is annoying, I grant you. It's a bother to have to, but I have to practice now how to write a whole new symbol. Yeah, it is annoying, right? And I had to dedicate 5 minutes of my life back in college to practicing. How do I make this symbol, right? And it's humiliating, right? It's like I'm in elementary school again, learning how to write. Very bothersome, but yeah, you have to do it because, again, if you write it with if you write it with an English D, it is just straight up wrong, and if you write it with a delta, it is straight up wrong. Okay, how are we doing? Is everybody okay? Everybody with me? Okay, another notation to be aware of is this subscript notation where you put the symbol. The variable that, the one variable that you're treating as being a variable, you put that down there as a subscript. It's vaguely Newton notation-like. Not exactly. It's a subscript instead of a superscript. But also very common, and it has its moments. So you're definitely going to see both of these notate. Well, all three. I mean, this one's really kind of the same as that. You're going to see all of these notations, so heads up for all of those. Okay, and let's do one. Let's start with a really hard one. That looks like a monster. Look at that. It's a product of three factors. One of these factors is a composition, the inside of which is itself a product. Right? Yikes. This looks like I'm going to have to use the product rule several times and the chain rule a couple times. Oh, probably the product rule again. This looks like it's going to be super inconvenient. This is actually a super easy partial derivative. And the big point, make sure to remember, when you are doing a partial derivative, you are holding all the variables constant except for one. So looking back here, you see I am taking a partial derivative with respect to y. Y, therefore, is the only of these variables that is acting as a variable. It's the only one of these variables that I don't just choose to view as being a constant. That means x and z, constants. Which means that's a constant, which means this whole factor is a constant, and that's a constant, and that means that's a constant, and that's a constant, which means that's a constant, which means that's a constant, which means this is a great big ugly constant. Massive constants. Most of this expression, constants. Everybody see what's going on there? So the remaining, like the actual work here is not much. This great big massive constant, as multiplicative constants do, just kind of comes along for the ride. And the actual action of taking a y partial of y squared is easy. Partial of y squared with respect to y is 2y. Boop, done. Everybody on board? Gotta love it. Nice and easy. So I nominate, by the way, partial derivatives as being the easiest derivatives to compute, and I am including single variable derivatives in that list. Because when you're taking single variable derivatives, you don't get this luxury of I just get to take huge fractions of my expression and just be like, you know what, I think I'm going to go ahead and view that as a constant, right? No such luxury in single variable calculus. So I think these are the easiest when it all comes down to it. And that is nice. A couple more examples. These feel weird, so I think they're worth looking at real quick. You look at this expression right here. Again, it looks like a monster. It looks like I've got a function to the power of a function, but I don't. What I have here is a partial with respect to x. That means x is my variable. That means all of this is not constant, but the other variables, in this case y, constant. That means this exponent is just a great big constant. So this is not function to the power of a function. This is function to the power of a constant. And then you have a, what do you call it, a power rule or something. It's, the chain rule combined with the, I guess we'll call it the power rule, right? So the old news as to how you deal with this. Yeah? Everybody happy? Okay. Likewise with this next example, looks ugly, but keep in mind, z is our only variable. So that's the only variable. X and y are constants, which means what I have here as my base of this exponential is a great big constant. And so this is basically constant to the power of z. And again, there's an old single variable calculus rule. Make sure you know all your single variable calculus derivative rules. Right? I know it's a while ago probably, but make sure you're good with all of those. They're going to come up. So, okay. All right. Okay, so let's summarize here. I made an arbitrary definition. Case could be made that this was a very self-serving arbitrary choice of a definition. I clearly rigged it up to be convenient. Is that you're allowed to do that? Can I just make a definition of something that I think is just convenient? Sure, go ahead. Free country, knock yourself out. It's fine. Define whatever you want. But it is therefore on you to show that it has any connection to the real world, any actual utility, any geometric interpretation, something, right? I still remember the combination of amusement and embarrassment when I was a kid. I thought that it was super weird that 4 times 7 would be 28. And I was like, what? Why? That's such a weird choice. I got an idea. How about this? How about we just agree that it's 47? Life becomes so much easier, right? Why not? Let's do that. Free country. I hereby define this as the Bray product. And I can totally do that, and I was absolutely free to do it. And now it's on me to give any justification for what this has to do with the real world. What can I do with this? Or did I just make up a bunch of nonsense? And in fact, here I made up a bunch of nonsense, obviously, right? So, but again, same story. I made something that was convenient, and just because I write down some notation doesn't mean that it actually is useful for anything, right? The fact that it's easy to compute doesn't mean squat in terms of actual applications to the real world or connections to pre-existing natural mathematical concepts. Nothing. So I have to figure, why is this actually useful or natural? And said differently, we want to talk now about what are the geometric interpretations of partial derivative. Now I emphasize, again, y'all heard me give the big speech last time. It depends on what kind of a picture you're looking at, right? Calculus of graphs is going to be very different from calculus of level sets, which is very different from calculus of parameterizations. So let's be explicit. And so I'm going to be as explicit as I can. I'm going to do my best throughout this course to continually remind you, right? Probably less and less as time goes on, right? But nevertheless, I'm going to do my best to remind you as much as possible. What kind of a picture are we looking at? But it's also on y'all to keep that in your mind on your own, right? That when you're looking at a picture that relates to algebra, whoa, what kind of a construction is this? And you got to keep the calculus of graphs separate from the calculus of level sets, separate from the calculus of parameterizations, etc. Okay. Okay, so here we're going to look at graphs. So what we're about to do applies only to graphs. And you see here we have a graph, right? So we're looking at the graph of this function called f. 2 numbers in, 1 number's out. That gives us a surface. Okay. All right, so let's try to make some sense out of, again, in this graph context, let's try to make some sense out of a y partial. Keep in mind when you take a y partial, that is a 2-step process. We've already talked about what the various steps are of computing a y partial. Right, it's a 2-step process. And let's just go through and geometrically write down, what is the picture of each of those 2 steps. And it turns out it's actually pretty straightforward. Step 1 is to fix all the other variables. In this case, x is the only other variable. So, per the method, we fix x. And if I'm interested in, at some point a comma b down here in the domain where x starts off as being a, when I fix x, that means x will remain a specifically. And now, geometrically, what does that look like? Again, in the graph context, so what we're doing here only applies to graphs. X equals a is a plane. Specifically, it's a vertical plane, and specifically, it's in the y direction. Now, this is confusing. It's easy to kind of get it backwards. Again, I urge you, please do not try to don't make semantical conclusions. Right? It's easy to look at this and be like, oh, okay, so the variable x, okay, so this must be in the x direction. Nope. Just look at the picture. It's clearly not. Right? X being constant means that we're looking at a vertical cross-section in the y direction. Geometry is right there looking at you, right? So don't think about it semantically, draw the picture, think about it geometrically. Yeah, everybody see the point there? Easy to mess this up if you look at it the wrong way. Okay, so taking a vertical cross section. Okay, well, wait a second. Let's slow this down. We were taking a vertical cross section. We started off with a graph. The graph was this whole surface. But when I take that vertical cross section in the y direction, the result is now I've got just a curve. So step one, geometrically, is we take a cross-section of our graph to look at a curve. Okay. Step two. Oops. Yeah, do like this. Step two, and keep in mind, this was our cross-section curve that we just talked about. Step two says take the derivative with respect to the variable you're taking the partial with respect to. So we're going to take the we're doing a y partial, so here we're going to take the derivative with respect to y. Okay, well, yeah, but, right, I mean, what I have is a function of just y, right, because x is constant, x is stuck at this value, a, whatever that value a is. And so if I take the derivative with respect to y, that says, all right, as I proceed along in the y direction, and geometrically, how do we interpret taking the derivative when you're looking at a curve that is the graph of the function you're looking at? And we have this existing interpretation, and that is the slope of the tangent line. Thank you, Calc 1. So that's a nice punchline. It's actually pretty straightforward and simple. If you want to take a partial derivative with respect to y of some function, great. Slope of the tangent line, just like in single variable calculus. Kinda. Now, important distinction, two important distinctions. Easy to sweep under the rug, and don't make this mistake. When you're taking the partial with respect to y, you get the slope in the y direction. There's a bunch of different directions through which you could take cross sections. The y partial gives you the slope when you take that cross section in the y direction. The other important asterisk here, this only makes any sense at all if you're looking specifically and only at the graph of that function. So this is calculus of graphs. It's got nothing to do with level sets. Okay. Now, as an exercise for y'all to think about on your own, you can reason through very analogously. Nevertheless, you got to think it through. Draw the corresponding pictures. The pictures will be similar, but importantly different. Persuade yourself that the x partial is the slope of the graph in the x direction. Now, again, I know semantically, I mean, very much exactly what you would expect. Right? But don't rely on that. It's very important to think through step by step. How do you know that this is through? So excellent exercise. Again, come talk to me in office hours if you have any questions about that. Okay. Let's see here. Real quick last thought. Just for contrast purposes, again, you know, there's this tendency for students to sort of cling too much to the idea of graphs because that's how everything in single variable calculus works. It's all graphs. Pretty much, right? So let's, though, think now about this literal picture. Not a graph, but domain over here, target over there, functions take stuff out of the left and into the right. In this context, how do I make sense out of a partial with respect to y? And, okay, well, if we're taking the y partial, then x and z remain constant, which means that I'm moving only in the y direction. because x is fixed and z is fixed. And having made that observation, how do you think about the derivative? What is the single variable derivative of this function of the single variable y? Well, the derivative, again, is the thing that you multiply by input changes to get output changes. And so you might say that, when you're looking in this literal picture sort of interpretation of what a function looks like, y partials you interpret as, okay, for a per unit distance that you go in the y direction, correspondingly, by what factor do you move more or less in the output? Notice, not a slope. No slopes. No curves or surfaces of which to take slopes. Right? It's completely different geometric interpretation here. Right? Because we're not looking at graphs. So in this, again, very useful picture that we're going to be seeing a lot of this kind of picture. This is a very natural picture to draw. This is how this is a way that I think the natural way to make sense out of partial derivatives in this context. And I'm sure I'm out of time by now, so we'll draw the line right there. Y'all have a good rest of your Wednesday. See you Friday. Oh, and a reminder, if you came in after I did attendance, you got to get marked down. So stick around, come talk to me, make sure that I mark you as present. Because if you if I didn't specifically do that with you when you were coming in, you're not marked down yet. Okay, see you soon. I was so